Now we're going to talk about something called concavity, okay? So we say F is concave up if F prime is increasing over I. How do we know if F prime, the first derivative, is increasing? Well, we look at the sign of the second derivative. So if the second derivative is positive, then we say the function is concave up. All right. If the second derivative is negative, guess what we say? Second derivative is negative. Then we say the function is concave down. Because second derivative being negative tells us that the first derivative is decreasing. So that's what we call concave down. So let's take a look at this in an example. But I do want to talk about one more point, okay? The concavity, like where it changes from concave up to concave down, or from concave down to concave up. Where this concavity changes, this is what we call the point of inflection. Now look, the concavity changes when the second derivative goes from positive to negative or negative to positive. So what number do we hit when we go from positive to negative or negative to positive? 0, right? So point of inflection is when the second derivative is equal to 0 or when the second derivative does not exist. We will do more of this in section 3.3 when we work with rational functions. But today, on our polynomial examples, if you want to find point of inflection, you will set the second derivative equal to 0. I'm going to set the second derivative equal to 0 and solve for the critical, or not the critical value, the x value that will make this happen. So just gave you lots of information. Concavity, like concave up or down, and how to find the point of inflection. So let's go look at an example together, okay? So the same example that we've been working on, but part 3 is asking us to find, give the coordinates of any point of inflection, and identify the interval where the function is concave up or down. So I'm going to group these two sections, two parts together in this video. So let me copy this function because we did a lot of work, like all that relative minimum, maximum work. But maybe over here, down here, I will do the concavity work, okay? Now, when you want to find concave up or concave down, or point of inflection, you have to find the second derivative. Well, we'll start with the first derivative. That is 3x squared plus 6x minus 9. Now keep going, do one more step. Find that second derivative. That is 6x plus 6. Now what you're going to do is set this equal to 0. Set it equal to 0. That's how you find the potential point of inflection point, okay? Subtracting 6 from both sides will give me negative 6 equals 6x. I can divide both of these by 6. So we got the x value to be x equals negative 1. So, but I'm not going to say this is the point of inflection. This is a potential point of inflection. So what you do now is get your number line, put that candidate in the middle, and what we're going to do is we're going to check the sign to the left and right of this potential point of inflection, okay? So let's check the sign of the second derivative by plugging in. What is a number that is to the left of -1. What's a number that is smaller than -1? -2. So if I plug in -2 into the second derivative, I will get 6 times -2 plus 6, which is -12 plus 6, and that's -6. Look, second derivative just came out to be negative. This must be concave down. All right, this time we're going to plug in a number that is bigger than -1. I'll plug in x equals 0 because 0 is bigger than -1. What's going to be the sign of the second derivative if I plug in 0 here? So 0 plus 6, that's positive 6. Positive second derivative tells me that this interval is going to be concave up. Now notice concavity changed to the at -1, right? So this tells me that -1 is where the point of inflection happens. So let's write down our answer, okay? So we're gonna say concave down on -infinity to -1 and concave up on -1 to positive infinity. And we have our point of inflection at -1. Do we know the y value? I don't know yet. So we're going to have to now go find the y value of x equals -1. So this is the function that I need to plug in x equals -1 into. So let me open a calculator here, and I'll just plug in -1. -1 cubed plus 3 times -1 squared minus 9 times -1 minus 13. Well, the y value came out to be -2. So the point of inflection is at -1, -2. Okay, so I did have, I think I just erased the graph, but I'll re-answer the question, but let me go ahead and show you the function. Let me try to go back. Let's see if I can just click like this. Okay, here's what we got. This graph is so skinny. Let me see if I can try to change the y-axis scale a little bit so that doing something real quick. Right, look at this for me. Point of inflection. Where is it happening? I will plot this. I will plot our point of inflection at -1, -2. This is where the concavity changes. To the left of it, this is concave down. And to the right of it, this is concave up. And I don't think I ever actually showed you an image or a picture of concave up and concave down. We just talked about how that is where the first derivative is decreasing and the first derivative is increasing. But I will go over some examples where we look at what concave up or concave down look like in graph. But I think of these as just frowny face for concave down and smiley face. Like I'm looking at I'll show you the picture that I'm going to go over on another page. So over here, this is an image of concave up. Okay, this is gonna if the graph looks like this is gonna be concave up. So on our graph right here, you see this part of the graph is concave up, right? Concave down is gonna look like an upside down U. Okay, this is going to be the concave down graph. Okay, so you see that right here, right? This is concave down. But we'll do more examples of picture reading or graph sketching on another page. But on this example, we've finally finished this a single problem. You see, it asked us to do lots of it, but the last part was using the second derivative, setting it equal to 0 to find the potential point of inflection. Check the sign to the left, check the sign to the right to see if the concavity really changed and calling that a point of inflection. So this one, it all involved the second derivative, but this is how you can find the intervals where the graph is concave down or up and the point of inflection.